So, as promised, today we will look at vertical circles. Ryan, as you wander out there, you can just kick that very close to it. Wander back. I think so. No, I know. That's the problem. I was just handing them out while I was waiting for that to load up. So. Okay, so what we've done up to now is we've dealt with uniform circular motion. Right? So I started you off with example number one, simple one like this. The example that we looked at yesterday was, we talked about the braking force in the string, and it was based on how much weight, how much mass you could put at the end of the string, right? And so it had the word vertical in the circle, but really all it was a fancy way of saying the string will break when it gets to such and such force, right? Okay, so today we will look explicitly at tension problems for vertical motion. So we're going to be looking at motion like this. Now, the U in UCM refers to what? Uniform. I think I've already sort of started this conversation, but let's sort of go into a bit more depth. Is the motion uniform when it's vertical like this? No, it's not. Correct. Because if I slow it down, there's some point here where it actually stops being actually circular motion, right? Which implies there's also a decrease in speed on the way up and an increase in speed on the way down. So it's not technically uniform. Do the formulas still hold true? Yes, but you have to sort of average things out a little bit. Okay. When it's like this, the velocity is constant, right? And it's an average velocity, except the average is equal to that one number and it doesn't change. It's always the same, right? Like the initial velocity here is the same as the final velocity there, right? And it's equal to the average because it's all the same number. Whereas here, it's sort of different. So you have to sort of deal with that as well. Where is the tension in the string the greatest? Where is the tension in the string the greatest? On the top, on the sides, on the bottom. Sounds like you don't really know, and that's okay. Like when the object is at the top, when the object is at the bottom, or when it's
right there.
One of the sides. Why do you say the sides?
I don't know. Pulling it over.
You know what I mean?
It's the force to swing it up.
I just have a feeling.
Okay. Describe the tension in the string at the top.
Pretty loose.
Pretty loose. In fact, if it's going slow enough, the tension might even be 0. So are we agreed that the least amount of tension is at the top? Would not logic say then that the greatest amount of tension is at the bottom?
Don't always follow logic.
Yes, I know that. When is it going as fast as Steve? Here? Like right here, we've agreed it's going at slow to the top, have we not? Okay, speeding up, speeding up, speeding up. Gravity's accelerating it, so shouldn't it be going its fastest right at the bottom? And isn't the centripetal force, Fc, equal to mv squared over r, which would mean that if I've got a greater velocity, I should have a greater tension, of course. So unfortunately, Steve is wrong. Where is the tension the greatest? Is there some critical velocity? Yeah, we saw that in the video. In fact, if you were here, you guys were all here, right, when I showed you this?
Huh?
The one where the guy drove the car?
Let's watch it. Refresh my memory.
You know, where the guy drove the car and the big giant loop-de-loop?
I feel like I still remember that one.
We saw the guy with the balloon in the car.
Yeah, no, I haven't seen this one.
And the Oscar goes to Braden because he can't keep a straight face, smiling away there. I will tell you this next little formula derivation drives students crazy. They don't like it.
Oh.
I will say this. We are already determined when the tension is greatest. When is that? At the bottom, okay? So keeping that in mind, just go with the flow a little bit and make sure you understand that. If you would get that, you'll be good.
Did you just add on to the formula sheet from last time?
You can if you want. It's up to you.
Would that be weird to do?
It's up to however you want to do it.
Sometimes.
I know. You decide. It's your notes. Your job is to learn it Your job is to figure out how you want to
How
organize it,
many
right?
formulas are there?
I think it's 2 today.
Okay.
Okay, so I ran that little animation there for you. What do the blue and the red and blue arrows represent? You see the acceleration and tension? Which one is the tension? The red one? And the red one, what would you say about its direction?
It's in.
Towards the center, right? And when is the red arrow the longest? At the bottom. So the red one represents the tension. What does the blue arrow represent? What do you think? Gravity. And it's always down, and it's always relatively small, and in fact stays the same, right? Because it's always down, it's always 9.8. Okay, so what happens to the speed of the ball? At the top, it slows down, and then it speeds up on the bottom, right? What happens to the tension in the string? We've talked about this. It's greatest at the bottom, less at the top. If you want to jot that down, you can. String tension is greatest at the bottom, it's less at the top.
So would it be equal on both sides then?
Yes, it would. In fact, it would be, if I wanted to talk, say, like rough numbers, let's say the tension at the bottom is 100 and 50 at the top, what would it be on the other sides? Yeah, 75 and 75, right? That's exactly how it would be. Does that sort of kind of make sense to everyone?
Is tension ever going to be 50 at the top though? Like you said, it's going to be 0 on the top.
It's 0 when we're at that critical speed, right? But if I go like this, clearly there's tension at the top, right? It's 0 when I'm at that perfect speed, that it just falls apart, kind of thing, which is basically the speed that he went around the ramp at, right? Yeah, just almost fell off. Okay. Again, see the tension? What does it do? It gets bigger and bigger and bigger, and then there's this, what's this W thing here? That's the weight force, right? And as I speed it up, what's going to happen to the value of T? It gets bigger, right? Okay, and if I go down low, there's probably some magical speed where the tension is almost 0. How about if I go right to the bottom there? There, just, oh, actually, yeah, it disappeared, right? Okay. Okay, I think I've given you the basic idea. Let's delve into the formula. I would draw that picture. Okay? Draw that picture. This object is traveling in a counterclockwise direction. V and V. Okay? I've got FW, which we know stands for weight force. Weight force is at the top, weight force is at the bottom. You'll notice that the weight force in both cases points down. I've got FS1, FS2. String force 1, string force 2. Tension, right? String force, tension, same thing. Because of gravity, the speed of the ball is not uniform. Where is it fastest and where is it slowest? It's fastest at the bottom and slowest at the top. I'll give you a moment to get that down. Okay. At the top, the string, the centripetal force, FCT, total centripetal force. Let me just make that a bit bigger. The total centripetal force is made up of the string force, right, FS, and the weight force. You'll notice that they are both pointing down. Right? And the string force, sorry, the centripetal force is mv squared over r. The v is at a minimum. Right? So I've got mv min squared all over r, and that's equal to the string force. All I did was I took this and I stuck it in the middle there. That's what I did there. Right? And I said that the centripetal force, mv squared over r, is equal to the string force plus the weight force. And FC, FT, and FW are all down. Right? What's it look like at the bottom? It's different, right? FCB, centripetal force at the bottom.
What is that? SC what on the top one?
FCT,
Is T? Oh, so
centripetal force at the top.
Okay.
How about pencils down, let me explain. I will promise you I'll give you time to write. It really works better if you just watch. String force T, or sorry, centripetal force T, total centripetal force is mv squared, where v is a minimum, over r, and that's equal to the string force plus the weight force, and they're all down. At the bottom, FCB, centripetal force bottom, is made up of string force at the bottom plus the weight force. But the v is at a maximum, right? mv squared, v is a max, over r is equal to the string force at the bottom plus the weight force. FC and FT are up, right? FW is down. This one is down. FT, total force. String force, that should not be an FT. That should be FSB. I changed this here and I didn't change this one here. SB. String force bottom. This one here should be, yeah, I see what I did there.
So is it FC? That's the FCT or whatever?
FC is centripetal force top. FST, string force top. FCB, centripetal force bottom. FSB, string force bottom.
What did you write?
I just changed these FTs to, I changed that to SB, and I changed this one here to FST.
So FCT is top, not total.
Top. Top. Okay. Do you agree that the Vmax is greater than the Vmin? By definition, yes. Therefore, I prove the string tension is greater at the bottom. FSB, I made a change and I didn't follow it through. FSB must be greater than FST. I proved it. Do you need to write down the proof of it?
I'll trust you.
Yeah. You know I proved string force is greater at the bottom, right? I'll pause there if you want to write something down. So again, this implies there's some velocity below which the ball will not move in a circular path. The string will slacken to the ball's highest point, and what will happen? Well, that will happen. That's what could have happened, right? That's what could have happened. This guy wasn't going it up. He didn't have enough centripetal force. Now let me ask you this question. When I do the rubber stopper thingy, what's providing the centripetal force? Well, and the force in the string, right? There's a tension, causing it to travel in a complete circle. There's no string there. There's no string in that real life thing. What's supplying the centripetal force holding the car in a circular path?
Friction on the thingy, the wheels. On
The classic thingy.
on the weight of the car.
Even when it's upside down, right?
Yeah. Friction. Friction on the ground.
It kind of blows your mind a little bit, isn't it, right? It's hard for me to explain, too. But basically, it's inertia. The car, because of inertia, the car is pushing against the ramp, which means by Newton's second law, the ramp, the loop-de-loop must push back. And so that's what's causing it to maintain that circular path, right? It's the normal force, and I use air quotations there, because it's really the reactionary force to inertia, which isn't really a force. Makes my mind blown just trying to explain.
Is this an actual formula?
This is an actual
Oh,
formula.
V equals U.
And if you noticed, it might even have been in the video, right? The minimum force. Let me go through it, and then I'll give you a chance to write it down. The minimum value is when the string tension is 0, right? String tension is 0. At this ball, the ball just makes it around. So this FST string force becomes 0, and mv squared over r is equal to mass times gravity. And look, my friends, what happens to the letter m? Did the mass of the yellow car and the mass of the sun driver matter? Did not. Doesn't matter how big you are. The minimum critical velocity, as they call it, for going around, v squared over r is equal to g, so the velocity is equal to the square root of rg, and it was over the guy's shoulder there on the board. I saw it. Did you see it? I pointed it out the other day.
Wait, so
I did point out the other day. I forgot to do it today.
R is still radius?
R is radius. And g, of course, is 9.8 on Earth. If you took that loop-de-loop to the moon where gravity's 1.6, would you have to go faster or slower? To just barely make it around.
Floor.
Slower?
Yeah.
Faster. Slower? Yeah, it'd be slower. How come?
Because r times 9.8 the square root is going to
Be a smaller number, right? The g would be not 9.8, it'd be 1.6, which would make that smaller. Square root the whole. So you could actually, could you then do the loop-de-loop easier on the moon? Way easier.
So the minimum value is the minimum force.
Minimum speed, Vmin. Critical speed for making the loop-de-loop. How fast do you have to go?
maximum speed where it doesn't work.
Whoa, man. Oh, you gonna go back to that?
Yeah, I'll go back.
Okay.
Is there some maximum speed? No, you just go around really fast. But in the case of the real driver, what was the danger of going too fast? Too much g-force, right?
They talk about the tail dragging too.
Yeah. Yeah. So the critical velocity is equal to the square root of rg. The mass does not matter. Critical velocity. It's that minimum speed that you must go around, right? You've all played with Hot Wheels, you know that you got to put it far enough up the ramp so that it goes fast enough to make it around. Have you done the mini golf where you putt it and it goes around like that, right?
Oh, I
And if you don't putt it fast enough, it's not going around, is it?
You always just got it.
Yeah. You got it. Pops off, bounces around, hits some rock, comes back and hits you in the foot, right?
Playing out some eyes.
Yeah. What was that?
If you're in the wrong, you got to hit it.
I'm trying to remember a story. I was at mini golf there in Winnipeg one time. A friend of mine did that very thing, and I think he hit a rock, and I think it bounced and it went like over the fence and into the parking lot and onto the highway, I think, or something like that.
Got to play it in his eyes.
Can't remember. How did that go now? I'll have to phone him tonight, ask him if he remembers that. Okay. This value of Vmin is called the critical velocity. Depends only on the radius of the circle and the acceleration of gravity. It does not depend upon the mass.
So can you say that we're never going to include math in these formulas now?
I might throw it in there and see if you know that it doesn't depend upon mass.
I'm going to put a little star on
Yeah, it does not depend upon mass. Now, if you happen to work for Nortel or Bell or whoever, and you put a satellite into orbit, what speed does it have to orbit the Earth at? The critical velocity. Because if it's not going fast enough, John, as it orbits the Earth and it's not going fast enough, right, what's going to happen? It's going to eventually degrade and fall to the Earth, crash and burn and cause problems. And if it's going too fast,
It's going to end up in the...
because like if I go too fast here, all that happens is I might break the string, right? But if it's going too fast as it's orbiting, what's holding it in orbit? Gravity. And if it goes too fast, then it's going to be
Oh my god.
gone.
Mars.
Gone.
Okay, what the Vmin, is that going to be like part of the question? Is
Yeah, oh yeah, I'll for sure I'll ask you about Vmin.
Vmin is critical velocity?
Yes. Okay, let's do a sample question, shall we? Let's do that third sample question, and then I'll be quiet. 'Cause I'm done. I'm tired. Had a long day.
Oh, these are...
These three, yes, you've got three. We've done sample 1. We've done sample 2. Let's have a look at sample 3.
And what?
Is it equal square root of RG?
Yep. That's the critical velocity one, right? Okay. So, in this particular case here, we've got a 0.5 kilogram body. It's moving in. Now notice that I quite often use this UCM reference, even though it's a vertical circle. Okay, so I point out it's not really uniform. We just say that.
Oh, that's stupid.
It is stupid. I should probably call it a vertical circle, right? It's not uniform. I should probably stop saying that. So it's a radius of 1.5 meters. The period is 0.5 seconds. Find the speed of the body in its orbit. Find the centripetal force needed to maintain this motion. String tension with the mass at the bottom, string tension at the top, and I'm going to throw one more in there. The critical velocity to maintain motion. Will it recognize that?
What?
Pretty close.
Okay, what was the actual question? Oh, 610 City.
To maintain buildings.
Yeah. There, is that better? Okay, so job number one, the speed of the body in its orbit. How fast is it going? Let's draw a picture. What's my radius? 1.5. My mass? 0.5. My period is 0.5 seconds. It takes 0.5 seconds to go all the way around.
At a circle?
Yeah.
Okay, that's good to know.
How's that? Okay. How fast is it going? Now, speed is it's always going to be, at some point, you're going to be able to relate it to d over t, right? Distance over time. We know the time. It's the period. In this case, it's going to be 0.5 seconds. But what distance does it travel? It's going around a circle. 2 pi r, the circumference. 2 pi and the radius, 1.5. Again, the arithmetic is never hard. It's trying to figure out what to do with it, right? 18.8 meters per second. 2 pi r over t.
So what was the point of doing that B equals C with cheating? You could have just used the formula initially.
I wanted to show you I'm reminding you where this comes from.
Oh, okay, that's good.
Okay, just reminding you that it's circumference over time. Now, average centripetal force needed to maintain this motion. Average, because we know force at the bottom is going to be greater than force at the top, right? So average force, and then we'll step back and we'll figure out the force at the bottom and the force at the top, right? So the average force, Fc is equal to mv squared over r. Oh, I should ask you this. I guess really this A, is this speed, this 18.8, is that constant? It's not, right? So this is actually average velocity, is it not? Right? So the average force, it would follow, is based upon the average velocity, right? So mass, 0.5, velocity 18.8 squared all over r. (118 newtons). Force is a vector. It should have a direction. What direction is the force? Say again? I did draw a circle, then you laughed at me, so then I had the computer draw a circle. What's the direction of the force? Remember, this is the average force, too. Is there anything in the question about north, south, nothing like that, right? So, what are our options here?
Horizontal.
No. Up and down, right? Okay, so towards the center, Ryan, is the correct answer. The centripetal force is towards center. You say that too? There's no way it's going to recognize that.
Turning center?
Toward center.
The nice one behind.
Right? Okay, now. Oh, you got to go, right? Okay, you go if you have to, man. I'm going to record it. String tension when the mass at the bottom. Is it going to be more or less than 118? It's already. Is the centripetal force, is the string tension at the bottom going to be greater or less than 118 or equal to 118? We've already established that the tension is greater at the bottom, haven't we? Okay, so
What is that though? That's a total tension?
that's the average. That's that 50 on that circle I showed you before, right? How much more? Well, let's look at it this way. I will explain. Let's look at it this way. The net force, F net, is enough to maintain, we'll call it UCM for lack of a better term. I guess VCM would work, vertical circular motion. Okay? So that means that the net force is equal to 118. And that total centripetal force, that F net, that 118, is equal to the tension, string force, Fs, plus Fw. And I have to be very careful I write this correctly here. Now, we are doing the bottom here, right?
Okay, what is FS? Is it S?
String force, tension, string force. Which direction is the 118 specifically at the bottom of the loop? Up, right? The 118 is up. It's pulling the thing up. So this is going to be plus 118. Okay? So I've got 118 is equal to, I'm solving for the string force. My weight force is my mass times gravity. Which direction is gravity? Down. Everybody with me to there? Sorta, kinda, maybe. And when you take that minus 4.9, it goes to the other side, it becomes. And therefore, the string force, the tension, is 118 plus 4.9, or 122.9 newtons. Is that bigger than 118? Yes. Does all of that logic hold true for the top of the circle as well? Is all of this true at the top? Absolutely. So how then does the Fs get to be smaller? Any ideas? There is a subtraction, but what change do I make to all of this? I'm just going to do this. I know you guys can't do this. No, I'm not. I'm going to copy it. I'm going to paste it to the next page. Are people done here? Whoopsie. Can I go past this? What change do I make? At the top, is the weight for it, is the 0.5 times 9 is it still minus 9.8?
Oh, because it's going down.
Gravity's still down, so what changes?
Negative 118.
Negative 118. How come? Centripetal force is now down. And so now, when I take that 4.9 to the other side,
John said it first.
John said it first? Yay for John. It's now, and I do apologize for that cut and paste, but I think it's effective for you to see it, that it's the same logic. So it's now minus 113.1. And you could say that the string tension tension I don't think is actually a scale or a vector, right? Because it's tension in a string, but the force itself is down. So what's really happening is this 4.9 newtons, the weight of the object is pulling it down, which means that the string has to do less work. Does that make sense? The string has to do less work. Now, if you want to
But why is it
massage,
at the top when it wouldn't be at the bottom?
but the object is at the top, Hannah.
Yeah.
But which way is the force pulling?
Yeah, but what if it's
Down.
at the bottom still? It's still pulling down even if it's...
No, because when it's at the bottom, that F net is up, right? The 118 is up at the bottom, positive, and at the top the 118 is down, negative. Yes, Hope, I've explained that? Thank you. I do agree it's not the easiest thing to get. I do understand that. It's a hard thing for me to explain to. Quite often I have to sit and think about it before I teach it, and I didn't do that today. I probably didn't give you my A+ game. Maybe about a B-. Do be aware that the force must be greater at the bottom than it is at the top, right? Like, you can make it work out.
Like, do you have to just say FS for both, or would you do FSB and FS?
You could do that if you want to additionally label it with top and bottom. You can, Hannah. Yes, that's true. Yeah. I honestly think if you sit down tonight in peace and quiet of your own home without your phone and TV and whatnot there, and you have a good look at it, you'll go, okay, yeah, I sort of get that. Yes, Jason.
So what would happen if weight force was greater than the F net?
Ah.
Would that mean, like, is that when it would not do
I don't think it, yeah, exactly, right? That would be when there's not enough string force at all, and it would, you're right,
It's just going off.
it would just fall. Yep, real good question. Okay, so we know this object is going, we know the average speed is 18.8. What's the critical velocity in this case? I added that in there. Is it going to be more or less than 18.8? Less is right. What is the critical velocity? Square root of RG. The mass does not matter. What's my radius? Is it 1.5 or 1.5? I got 3.8. Good timing. Any questions there? I get it, it's hard. It's not easy. You need to practice. Trust me. You got that first set, I can't remember the picture, it was on the right hand corner.
Biker.
Biker? No, the one from the other day.
There's no right hand corner.
Oh yeah, the one with the record, yeah. The one with the little record player there on the side. Okay, so you've got those. You can now do those ones that you've X'd out, 12 and 9. Okay, I gave you this not because I'm a jerk. Okay, I don't know, I had to run off and I thought, okay, I'll get that and I won't lose it, right? So put this in your package. I'm giving you the rest of this period. I'm going to give you all tomorrow.
I won't be here Friday.
Okay? You need to practice these. They are not easy. Okay? Find the solution. Oh, I know I have solutions to these.
Yeah, they're on the page.
No, solution. I know I have, are there solutions at the QR code here? No?
Yeah, no QR code. You haven't been QR code.
I will try to find those for you. I know they exist. We have to talk about G's as well. Like, for example, number 8 here. See this one right here, number 8? Put a circle, star, highlight, whatever. That question we need to talk about.
This one?
Number 8 on page 2.
We can't do it.
Well, you can try it, but I want to have a class discussion. How about we plan to do that at about 3:10 tomorrow? Okay? You'll notice that there's coefficient stuff in there, like there, it's building, right? All that stuff we've done before just keeps building. Go.